Hello, chemistry class. Today we're going to do section 3 of chapter 16. It's really short, and it's on what are called colligative properties of solutions. I'm sure you don't know what that means. I didn't know what it meant before I started reading, but it's not too difficult. So, a colligative property is a property of a solution that depends on the amount of solute, not the type of solute. So, what is a solution again? Well, we have a liquid, like we'll just use water for example, but it can be any liquid. And a solution is a liquid with some sort of usually solid material mixed in it. So sugary water is a solution. The water is the solvent. The sugar is the solute, right? So I'm going to use those words interchangeably. Solute is what you put into a solution. Okay, so these deal with the amount, not the type. So what do I mean? Here's an example. Opacity, right? So the more food dye I add to a solution, the more opaque it becomes. And I have some, right? So I have water and I think purple food dye. If I just I'll do 2 drops and I'll stir it with my broken piece of spaghetti. So, come on. That was a lot darker than I thought it would be. So, it's fairly transparent. I don't know what's going to happen when I put that up to the camera, but there you go. I'll use my flashlight on my phone. So, it's got a certain degree of opacity to it, right? Well, if I add more of this to it, and I'm just going to go crazy here, then that should make it more opaque. It blocks more of the light. It's even harder at this point to see through. So I don't know what this is actually going to look like, but if I put my flashlight on my phone through there, I don't know, maybe the light doesn't get through at all anymore. That would be one example. Another example would be density. So the more material I add to a solution, the more dense it becomes. And it fundamentally doesn't really matter what I add to it, because adding anything makes it more dense. It doesn't matter if it's sugar or salt or purple food dye or what. Let's put the cap on that before I have an absolute disaster here. Okay, so those aren't the ones that the textbook focuses on. We have 3 specific examples. First is vapor pressure lowering. So maybe we need to review what the heck are we talking about. Vapor pressure is the pressure exerted by a vapor that is in equilibrium with its liquid in a closed system. What? Okay, so what's a vapor? A vapor is a gas, right? So here's the example I came up with. Soda has dissolved gases in it, CO2, right? But if you shake a soda bottle, you really won't see very many bubbles. It won't fizz until you take the cap off, because the container's closed. The trapped gas pressure, you got the liquid and then the little bit of space above it, that gas pressure pushes down on your soda, not letting any of the bubbles escape. But as soon as you relieve the pressure, then all of that trapped gas that you shook up can come out. So if you add what's called a non-volatile compound, so non-volatile means that it won't become gaseous, right? Like if I take water and I just dump sugar into it, put the cap on, shake it, take the lid off, nothing's going to happen because sugar doesn't turn into a gas, right? Those are the types of things we're talking about. Sugar, salt, whatever. So if you add non-volatile compounds, the vapor pressure of the liquid is lower, right? Meaning, if I had a container, like if I have some water here, if I had this glass of water and an exact identical glass of water in terms of amount of water, but in that one I dumped a bunch of sugar into it, and we just let these sit for several days, the one with no sugar in it, the water in it would evaporate quicker. Maybe we would put these outside so it wouldn't take very long. That's an experiment you can do at home. Take 2 glasses, same size, same amount of water. In one of them, dump either sugar or salt, put them outside, and the pure water will evaporate. All of it will evaporate before the other one. Let's talk about why that is. When you dissolve compounds into water, we can't see the compounds because they're extremely tiny, but a shell of water molecules will surround them. Those water molecules aren't available to evaporate. So this effectively means that there's less water in the container that can vaporize, so the pressure is reduced. And ionic compounds reduce vapor pressure greater than non-ionic compounds. So if you did this experiment with 3 glasses of water, you'd have the pure glass of water with, let's just say like 10 grams or like a tablespoon of sugar in it, and then another one with a tablespoon of salt in it. The pure water should all evaporate first, then the sugar water should all evaporate, and then the salt should evaporate last. I have a picture here, not a picture, I made a model here to try to illustrate this because it's kind of confusing. So here are all these water molecules, right? So it's just a liquid container of water, and the water molecules are just kind of randomly thrown about. If I add, for example, salt to this, sodium and chlorine ions, this is what happens. So if we go back and forth, here's the water originally, here's the water after those ions have been added. What you see is a bunch of water molecules surround and they form a shell around those ionic compounds. So that's what I mean by there's less water available. Those ones that are attached to the ionic compounds, it takes a lot of energy to pull them away. That's what causes the water to evaporate at a slower rate. So we go from this to this. Next is freezing point depression. So there's this thing called the Salt and Ice Challenge. I don't know specifically what it's called, but you've maybe heard of this. Do not do it because you can burn your skin, but you can watch dumb people on YouTube do this. So you take like salt and you shake it into the palm of your hand, and then you place an ice cube over that, and then you're supposed to squeeze it. And very soon it starts to burn your hand really bad because it's like if we put dry ice on your skin, which is extremely cold. That burns your skin. You can get a 2nd-degree burn from this. Absolutely do not do it. But let's discuss the science behind that. Adding a solvent, the reason it burns is because the ice cube is basically much colder than it normally would be able to be. Like if you did that with, you can do this with no salt, just squeeze an ice cube, it really doesn't hurt. Adding the salt effectively makes the ice cube colder, way below the freezing point, and so it burns your skin. Why the heck is this? Well, we have to go back to this model. So here are the water molecules when it's in a liquid state. They're totally random. But when ice freezes, it forms a crystal. So in order for a liquid material to freeze, oftentimes they have to form a crystal pattern, and they become neat and organized. Now, weirdly, it actually takes energy to do that. Even though it's getting colder, we think it's kind of losing energy. But again, if we add the salt, which we've done here, we can, oops, I went too far. We can see that the water molecules are now surrounding that those ions. And so again, it's hard to pull those water molecules away. That's what makes the freezing point lower. So next is, or the last one here is boiling point elevation. So if you add salt to water, it actually boils at a higher temperature. You have to heat that water up to more than 100 degrees Celsius. Why? Well, for the same reasons that the freezing point lowers. Some of those water molecules get wrapped around the solute particles, and it takes more energy to pull them away during vaporization. So it's also the same explanation for why it takes a glass of salty water to evaporate, or it takes more time for it to evaporate, because it takes more energy, and so it takes more time. In this case, we're talking about boiling, so we're talking about like an instantaneous vaporization. Well, you have to get it hotter than pure water in order to do that. And that's actually it. I know that's kind of quick. I talked about some demonstrations. I can't really do those demonstrations here, but feel free to do the ones I talked about. They're very simple. They don't make much of a mess. and it gives you an excuse to go outside. It's really nice out today. Hope you're doing well. Make sure you get the questions for this section answered and turned in on Google Classroom before midnight on Saturday this week. Take care.